let's talk about this idea of accumulators a little bit more. Right? We had just introduced this concept in the context of the reverse function, where we made this extra creative step of saying that in order to reverse a list, we're going to introduce a second argument to our function that is also of type list of A, that holds the result of the reversed list as far as we've already traversed the original list. And then in every step along the way, we simply take the first element of the list that we still have to visit and make it the first element of our accumulator. And so the accumulator builds up the reversed list over time, and once we reach the end of the list, we can simply spit out the accumulator, which then holds the final result. Right? So it's actually a little bit even like a variable that you change over time. That's one of the techniques you can use in Haskell if you want to simulate something like variables that change over time. You simply create a function argument, you make recursive calls, and in those recursive calls you change the arguments, and that gives you a little bit of the same flavor. So now that we've seen this put to good use in the context of the reverse function, we can of course ask ourselves, is this also useful for other functions? One function we can look at is, for example, the sum function, a function that sums up a list of numbers. Right? So let's actually keep that overloaded over the number type, right? So that we can apply it to different numeric types. Because the only things we're going to use are plus and 0, and both of these concepts are part of the num class, so this is the most general type we will be able to give. And if we apply the standard design pattern to the sum function, then we get definition that we have essentially seen before. The sum of the empty list is 0, and the sum of x cons xs is simply x cons the sum of xs. And I have to hide the sum function from the prelude so that we can define our own one. Okay. Now I'm going to do something slightly unusual. I'm going to start GHCI with a so-called runtime system flag limiting the stack size of the Haskell programs that can be run to a relatively small size, to 1 megabyte in this case. Typically, Haskell has a slightly different approach to the stack than many other languages. The stack that I'm talking about here is sort of the stack that one typically refers to for compilers. It's a data structure that is maintained at runtime while executing a program, where the program stores information about essentially return information for functions that you have called. Every time you call a function, you put information on the stack. And if you make recursive calls a lot, then the stack has the potential to grow. Not under all circumstances it will, but has the potential to grow. And one may run out of stack space. And in many programming languages, the stack is relatively small and of limited size. And that's one of the reasons why in many other languages recursion is strongly discouraged. In Haskell, in principle, the stack is allocated itself on the heap, and it can allocate more space for the stack when it runs out of stack space. So if you want, the stack space is effectively unlimited. And so there is no problem in itself with functions having a very high recursion depth. We still don't want code to take a lot of memory, though, if it doesn't really need to take a lot of memory. So it is interesting to sometimes think about this a little. And here, I'm artificially limiting my stack size to a relatively small amount so that I can demonstrate programs that do grow the stack substantially very simply, because then I'm just going to get a stack overflow exception rather than the program just eating up all my memory, which means that the video recording will get into trouble, and but it's hard to observe actually what's going on. Right, so I'm using this mainly for demonstration purposes here. And so now I can load my module. I did not actually pass the name of the Haskell file to GHCI, I forgot that, but you can also load something from within GHCI using the :L command. L for load, that reload only reloads the file that you already have loaded. If you want to load a new Haskell source file, you can use this one. And then reload works for that one that you have just loaded. And now I can try out my sum function, right? And if I try this on a small list, it just works as expected. And if I try this on a large list, let's try it on 1 million, up to 1 million, then I'm actually getting a Stack Overflow, right? Intuitively, if you think about it, summing up a list should not take a lot of space, right? If we sum up a list, what we expect to do probably, we start having a counter, right? And initially the counter is 0, and then we just add the elements of the list to that counter. So once we hit the 1, we change the 0 to 1, then we see the 2, then we change it to 3, because 1 plus 2 is 3, then we see the 3, then we say 3 plus 3 is 6, and then we update it to 10, and at every point we're essentially just holding one integer while we're traversing this list. And while the list itself can be long, it probably doesn't actually need to be in memory here at any point in time either, because we can lazily generate this list. So intuitively, the expectation is that summing up a list should be doable in constant space, and in particular also in constant stack space. And clearly, because we're getting the Stack Overflow here, that is not the case for the definition that we have. But we can actually also make that more precise, make it more obvious to us what's going on, simply by resorting to equational reasoning again. Equational reasoning being this process of step-by-step reduction that I have been introducing very early in the course as a good model of thinking about Haskell programs. And that applies also here, right? And we can actually do this with a really small list. Just we can observe the phenomenon very, very quickly that is happening without having to go to a list of size of 1 million elements or something like that. Okay, so let's actually just say we want to sum the list of numbers from 1 to 3. Okay, then remember that really this was syntactic sugar for an enum from to call, right? This list range notation is actually the same thing as calling enum from to 1, 3. So let's actually do this, right? Now, if you look at the sum function now, in order to decide between the two cases, we do need to know whether enum from to is a cons or a nil. Now, we haven't actually seen the definition of enum from to, but it is relatively easy to explain on the fly. Enum from to essentially just checks whether the first argument is larger than the second. If it's larger than the second, then we produce the empty list, right? But if it's not, then we produce a list that starts with the first argument and then essentially just goes to enum from to of 2 and 3, right? So it increments the first argument by 1 and then goes on like this. Okay? So at this point, we can pattern match for sum, right? And we can see that the second case applies. Again, lazy evaluation says we are not going to look at enum from to 2, 3 just yet. We're first reducing the outermost call, which is the call to sum. At this point, we get 1 plus, and then the sum of the rest of the list, which is enum from to 2, 3. Okay. Now we are in the same situation as before. We have to reduce enum from 2. So we get 1 plus the sum of, and now we get 2 followed by enum from 2, 3, 3. Okay. And now again, the second case, the second equation of sum applies. And now we get 1 plus, and now I'm going to put explicit parentheses here in order to make that clear, because this whole thing is the second argument of plus, and it remains, the result remains the second argument of plus. And we get 2 plus sum of enum from 2, 3, 3 at this point. And here we can spot what's going wrong, because we can't reduce 1 plus 2 now at this point. We have the knowledge about the 1, we have the knowledge about the 2, we know that we want to add these two numbers to something, but in both cases we don't have the other argument, right? Plus needs both the left and the right argument to be numbers in order to actually compute the result of the sum. But the right argument of plus is still this computation, which isn't completely evaluated to a number. And the right argument of this plus here is still this computation, which is also not completely evaluated. So we have this stuff in memory, this idea of, oh yeah, we have to add 1, we have to add 2, and this is exactly what adds, like what uses stack space, right? Like remembering that we still have to add 1 to the result, remembering that we still have to add 2 to the result, and we cannot make progress here, right? And in fact, we have to traverse the entire list and build up this huge chain of additions before we can make any progress. Fortunately, this list here is not too long, so we can actually go one step further now. So we get now that enum from 2 reduces to essentially 3 to enum from 2, 4, 3, right? And at this point, we can reduce sum again. So we get this, and we get 3 plus with another pair of parentheses, and then we get the sum of the rest. Okay, and then here enum from 2, 4, 3 is now fortunately reducing to the empty list, and sum of the empty list is reducing to 0. And here we have now reached a point where we can finally start reducing the additions, right? So now we can compute 3 plus 0 because we have both arguments of this plus. And we get 1 plus 2 plus 3. And then we can finally add 2 plus 3, and we get 1 plus 5. And then we can finally add 1 plus 5, and then we get 6. But we had to build up the entire chain of additions until we hit the end of the list, and only when we evaluate the sum of the empty list to 0, we can start reducing additions. And then, so we build up this huge chain, and then we can reduce it again. And this is building up, using up all the stack space in between, using up a linear amount of memory essentially for computing a sum. It's not terribly slow. It's also slower, but the main worry here is the memory use, right? It's not changing it to quadratic behavior. It's still linear in time, but it also means it costs linear space rather than what it should be costing, namely constant space. So that is undesirable. And if you think about what I said, the algorithm is that we have in our mind is to like have a counter that we update once we go. And that sounds very much like this accumulator idea. So perhaps we can just apply the accumulator idea to the sum function as well. Right? So let's write a new version of the sum function. And let's actually perhaps call the sum function that we had now, let's call it sum1, because we'll have multiple versions of the sum function. Okay. Let's call this sum1, and let's try to do the same idea as we had up here. All right. So we introduce a helper function, some aux, that maintains the current sum. Now the sum of the list that we have already visited, of the part of the list that we have already visited. So that should be something of type A, okay? In this case, not a list, but a number, okay? And then we have the list that we still have to visit, and then we have the final result. And again, this function follows the standard design pattern on list. So we have our accumulator, and we have our list, and we perform pattern matching on the list, so we get two cases. And if we hit the end of the list, then hopefully the accumulator holds the sum of the entire list at this point, so we spit out the accumulator. And if we are not at the end of the list, then we add the current element, which is the x, to our current accumulator and go on. So we call SumAux recursively, update the accumulator to be acc plus x, and continue processing xs. And then again, we need a wrapper function. Let's call it sum2, which has the original type, not the extra accumulator argument. And just like reverse was initializing the accumulator to the empty list, we now initialize the accumulator for sum to 0. Okay? Because that is the initial counter that we start with. And if we have an empty list, that will mean that we immediately spit out the accumulator and we get 0 as the result. So let's first see that this function still even behaves correctly. So sum2 of the empty list is giving us 0. Sum2 of 1 up to 10 is giving us 55. And now we do have a different algorithm, and there is reasonable hope that we do better, and we can try to call sum2 for 1 up to 1 million again. But unfortunately, we once again get our stack overflow, and that is perhaps quite surprising. Shouldn't this be much better? I mean, there is one thing. I mean, one question is that, like, of course we're still doing a recursive call in every step, and in some programming languages that is already enough to mean that we consume stack space. But this is a so-called tail call. A tail call means that essentially the outermost call on the right-hand side is a recursive call. That means that the function immediately calls itself again. There is nothing left to do after this recursive call on the right-hand side returns. And that means that it's a simple optimization, a so-called tail call optimization, to not allocate some stack space for such a recursive call. And actually quite a few programming languages implement this so-called tail call optimization. And Haskell does it as well. And so that's not the reason why this sum2 function still causes a stack overflow. So let's do equational reasoning again. Let's just look once again at sum2 of 1 up to 3 and see what happens. And once again, so that is just in a syntactic sugar for enum from 2, 1, 3. And once again, we have to evaluate enum from 2 in order to make a decision. Or, well, actually, now that's not entirely true. We let me actually rename SumAux also to SumAux2 to just because we'll have possibly multiple versions of this as well, to just make it clear that SumAux2 belongs to sum2. So here we're calling SumAux2 of 0 of enum from 2, 1, 3, right? And now we have to reduce enum from 2 a bit because SumAux2 needs to know whether the second argument is nil or cons. So again, we get 1 cons enum from 2 of 2 and 3. Okay. Now, what happens now? Now we know that the equation in line 41 here, that matches, and we replace the left-hand side with the right-hand side. And we may actually be tempted to gloss over this, but it is really important that we just replace the left-hand side with the right-hand side, literally, just applying the variable substitution. So let's do this. We get another call to SumAux2, and the first argument is the old accumulator plus x. The old accumulator is 0, and the x is 1, which is the first element of the list. And it's important for making it clear what the problem is that we really write 0 plus 1 here, because that is what we have here. Right? This is another function call, and this is not reduced automatically. And that is exactly what's going to be the problem. Okay, and then here we have enum from 2 to 3. Right? At this point, we have a call to SumAux2. That is the outermost function call. And in order to make a decision as to which of the equations of SumAux2 matches now, we still only need to look at the second argument. So we need to look further at enum from 2. We don't need to know what the accumulator is. There is no pattern matching going on the accumulator, nothing that would force us to evaluate the accumulator just now. And that is exactly the reason why Haskell leaves it unevaluated for now, because it is lazy, and we get 0 plus 1 here, and then we get 2 enum from 2, 3, 3. Okay. At this point, we can again see that the second equation of SumAux2 matches, and we can again perform the left-hand side to right-hand side replacement. And now we get the old accumulator, which is 0 plus 1, and we add to it the current element, plus 2, and then we still have enum from 2, 3, 3. And now we see that we have exactly the same problem, just in a slightly different place. Right here we built up some sort of right-nested chain of additions through all the recursive calls, and we had to reach the end of the list before we could make progress. Now we build up some sort of left-nested chain of additions in the accumulator, which in principle we could reduce, but since we are not forced to use the accumulator in any way, we don't do that yet, and that is unfortunate. Okay, and so this goes on. So if we go further one more step, we now get 3 enum from 2, 4, 3, and then we get SumAux2. And now we get 0 plus 1 plus 2 plus 3 as the accumulator, and enum from 2, 4, 3 here. And now we again are able to actually make progress, because now enum from 2, 4, 3 evaluates to the empty list. So now this matches, let me make this part here smaller so that we can fit it all on the screen. This matches line 40, right, at which point we just spit out the accumulator. And now the situation suddenly changes, because now we do have an addition, right, a nested addition. And that means that in order to make progress now, we do have to evaluate 0 plus 1. And then we get 1 plus 2 plus 3, and then we evaluate 1 plus 2, and we get 3 plus 3, and then we get 6. And we get the right result, but again, we have built up an entire chain of additions. Nevertheless, this is better than before, because before we could not have been making progress. We had a chain of additions where one of the arguments was actually not yet a number, so there was no way we could have reduced anything. Here, we do have additions that are completely ready to be reduced, and it's just that we don't actually need them yet that makes lazy evaluation ignore them for the time being. And this is one of the few places where lazy evaluation is a bad default in a way. And this is quite particular to this notion of accumulators, because the essence of an accumulator is that it is a partial result. You make updates on that result. So you use the accumulator to compute a new accumulator, such as here, but you're only using this result much later, namely in this case when you finish traversing the list. That's the place where we're actually returning it. So there is a long time between building up the computation and using it. That's a warning sign. And so this situation with accumulator is one of the few places in which we may have to tweak the evaluation order and may have to give a little hint to Haskell that it should actually be more eager to reduce something than it normally would be. And that is exactly the way out of this dilemma here, to give a hint to the compiler to reduce the accumulator. And there are multiple ways of doing this. And the classic way of doing this is a little bit tricky, I would say, a little bit subtle. And there is a more modern way of doing this, but that is, strictly speaking, still a language extension. I'm going to demonstrate the more modern way of doing this, and this is by means of a so-called bang pattern. And bang patterns are a language extension, so they are not part of the current Haskell 2010 standard. GHC supports them since quite a long time, but in order to make them available, you have to explicitly enable this language extension. There are multiple ways of enabling language extensions, but one simple way that is commonly used is to add a pragma at the top of your file. This time it's not an options GHC pragma, but a so-called language pragma. And then you list the language extension, the name of the language extension. And they all have names, and a BangPatterns language extension is just called BangPatterns. And just like the options GHC pragma, this has to be coming at the very beginning of the file before the module header, so that because it influences the whole way in which GHC is looking at the rest of the file, right, enabling certain syntactic differences even in this case. So it influences the parser and everything, so it has to be at the beginning of the file, cannot come somewhere further down. If we enable this language extension, then we can make a slight change only to our sum2 function. I'm nevertheless going to make a copy. And all the occurrences on the right-hand side should be changed from sumaux2 to sumaux3 as well. So the only change really is here in this accumulator pattern, which is just a variable. I'm going to place a bang on the two occurrences of acc. A variable, unlike a constructor occurrence, right, the cons or a nil, typically matches everything and signals that you don't need to know anything about this in order to perform this match. Right? If you want, even though there is just a variable being mentioned here, if you want some evaluation to be performed before accepting this as a match, then this is exactly what a bang pattern does. A bang pattern says can only match this accumulator if the topmost constructor of this value is known. In the language theory, knowing the topmost constructor of something is called a weak head normal form. Weak head normal form, sometimes abbreviated to WHNF. It's a very complicated way, or mysterious way perhaps, of saying something is evaluated far enough to know its topmost constructor. I'm saying this because the misleading pitfall is that people may think the bang pattern forces full evaluation of the accumulator. That is not the case. That depends on what type the accumulator has. In general, the bang pattern will only trigger evaluation up to the knowledge of the topmost constructor. Now, numbers are a bit of a strange beast. Numbers aren't really, they're more or less built-in data types. They aren't really defined by means of a data construct. They don't have constructors in the classical sense. You can, in a certain sense, look at all the individual numbers as being the different values that, say, the int type has. So you could look at the int type as a huge enumeration type with all the numbers being constructors. And perhaps inspired by this, we could normal form or knowledge of the topmost constructor, the outermost constructor for numbers, for integers, means knowing the number. So for integers, it does exactly what we want. It evaluates the integer up to the knowledge of the actual integer, and in particular, it will reduce any applications of plus as we want to, right? But if this was a list, it would only reduce far enough to know again whether this list is the empty list or cons. So that is a word of warning for using these bangs. We wouldn't actually have to put the bang on both these. I mean, I think putting it on one of these cases is enough, because then in order to make the decision here between the first case or not, we already have to look at the accumulator. But I think it's good habit to then apply it to all cases, so that you can locally see by just looking at one case that you'll definitely be able to rely on the fact that the accumulator is evaluated. So let's first observe that this actually has a difference, makes a difference. So if we call some 3 on this list of 1 up to 1 million, oh, it's still not in scope. Did I not reload? What's going on? Variable not in scope. Or did I not? I probably did not save here. Probably that is the problem. Yes. So this actually rather quickly returns the right result. Okay, so that is reassuring. And it does actually run in constant space. I mean, so it does not allocate heap space either, and we have made the stack size relatively small, so we would have got a stack overflow if there was still stack space used in depending on the number of elements. And in fact, I can put another factor of 10 here, which will make it slower because it has to do 10 times as much counting, but it will still work. Still okay. And let's, just for completeness, also perform equational reasoning once more here. And we can start just like we did for sum 2, because the definition is almost the same, right? Just to see where things go differently now. So we start with a call to sum 3, and that delegates to sum aux 3. And again, we need to evaluate the call to enum from 2. And then at this point here, right, we replace the left-hand side with the right-hand side. So we build up the 0 plus 1. But now, right, before we can decide that the second case matches, we actually have to reduce the accumulator again. So before we can make the decision between the two cases, now the bang pattern here forces that we evaluate the accumulator, just as the decision between the empty list and the xcons x's here forces us to evaluate enum from 2 one step more. So I'm doing these two things at once here, and at this point I'm back to the single number as the accumulator, and then I can perform the next reduction step. So rather than getting this, I'm now just getting 1 plus 2 of enum from 2, 3, 3. And then again, now the pattern match on sum aux 3 again, that forces the reduction of 1 plus 2 to 3, and the reduction of enum from 2, 3, 3 to 3 cons this. And then we get another match on the second case, which is giving us 3 plus 3 as the accumulator. And then once again, the pattern match on SUMAUX3 forces the reduction of 3 plus 3 to 6. And enum from 243 gets reduced to the empty list. And at this point, just get 6. Okay, and I've still been taking quite a number of intermediate steps to make it really clear what's going there. But we now see that all these things where we are doing most of our work, they have the same size, they have the same structure. There's always just one call to SUMAUX3, there is at most one addition, there is at most one cons, and so the total space use is easily seen to be constant. Even if we would make the list longer, up to 1 to 100, we would get a much longer reduction sequence, but the space we need to write down every line is constant. So that is a good indicator. Whereas here, we clearly see that it grows longer and longer before it becomes smaller again. And similarly, in the first version, the expression grows longer and longer before it goes smaller again. Right? So we have seen now that for the sum function, just like for the reverse function, using an accumulator is actually also quite an improvement, right? But we need to take an extra precaution, namely we have to make the accumulator strict by using a bang pattern, and then we actually get a version of the sum function that runs in constant space and is much more efficient than the original sum function that we would have used. In general, we're going to talk about this a little bit more in the next few videos, but in general, the right default for accumulators is to make them strict, right? Is to make to put bang patterns on them. Accumulators being these things where you build up the result, right? This pattern that we are introducing here, where you maintain a computation for a long time before you're finally using it. You can ask why didn't we need to do this in the reverse case? In the reverse case, we can still do it. We can put a bang here on the accumulator, and it does not make things any better or worse. I mean, it's still okay. If I reverse this list in my fast reverse function, it's okay. This is fast. This is again just limited by the printing speed, which is not very fast. It does not make a big difference because I said the accumulator is evaluated to so-called weak head normal form. That means up to the topmost constructor. What we put into the accumulator is always an application of cons, or here an application of nil. So there is always very clearly a constructor at the top, like at the outermost level in the accumulator already. So making the accumulator strict here does not make any difference in the case of reverse. It's not harmful, so that's why I'm saying it's the right default. Right? For accumulators, you should make them strict by default, essentially. But it is also not necessary in this particular case, because the accumulator is already in a weak head normal form at all times. We essentially only have the evaluated list, or the spine evaluated list, present at all times. Yeah, I mean, the other aspect is that, of course, reverse does also grow in space. I mean, so it does use a linear amount of memory to build up the reversed list before it spits it out. But that is unavoidable, right? We have to traverse the entire list up to the very end in order to determine what the first element of the resulting list is. So we have to build up the entire reversed list in memory. There is no way around that. So reverse will always cost a linear amount of memory, no matter what we're doing. But in this case, it's heap space and not stack space. So reverse even works for this large call with my limited with my limited stack size. nevertheless, I mean, so reverse is in that sense like a little bit odd, actually, that we don't really need the accumulator to be strict. It doesn't harm, but it doesn't help either. But in general, it's the right default. In the next video, I'm going to discuss whether, now that we've seen reverse and sum being examples for functions where the accumulator trick or design choice pays off, whether this is always the case, whether in fact all the list functions that we have been writing so far would be better written using an accumulator. And the answer to that is no. There are functions for which it is better to use the standard design pattern as we have originally used it. Otherwise, I would probably have started introducing accumulators even earlier. But we will try to figure out why and when exactly that is the case.